In this video I introduce the NumPy Array, which is our main vehicle to store data. The main benefit of NumPy is that it is an awful lot faster to run operations in NumPy than in pure Python. Arrays are much more efficient compared to other containers of data such as lists. The other area is vectorization. What do I mean by that? Vectorization refers to using arrays instead of loops. When you refactor your code, you can speed up the process very significantly by using vectorization. And we will see that several times, in particular once we go into simulations where speed issues arise. Now another area where I use NumPy a lot is built-in functions, like the square root, like the logarithm and so on. Yeah, so as a simple example, let me just define a as say 7 and b as 2, and then of course we can just simply apply a function to them, for instance a square root. Let me just do a print statement, and I want to now use the square root of say b. Yeah. So the square root of course now uses the NumPy package, and of course now you get here the error message because we haven't imported NumPy. Now we are working here on Spider, so this is here in this case referring to Anaconda, so NumPy is already there. So I just need to import NumPy as NP. Now very frequently when you start, for instance, putting data into an array, you want to first outline the dimensions of it. So as an example, let me just create now a vector, just call this a vector, which has all zeros. It's just NP zeros, and then I specify the dimension here. So for instance, let's put dimension 5. So it's a NumPy array, and we have now these 5 entries. It's all 0. Then I can also use an all 1 vector. So just call this 1, and I just now say this is NP once, and I put again the dimension here. Then I can update and change my entries. So for instance, I could refer to vector, and then using indexing I go into the first position and I just assign A, which I defined above. I can also use the same logic which we discussed in lists, -1, which is the last position, and I assign here a B. We can just run this, and you see we can update now our array accordingly. You can also assign arrays in one line yourself. Just call it now vector A. So what you note is we have a few brackets here, so you have to be a bit careful. So we have these normal brackets around, and then the rectangular ones indicating your dimensions of your array. So now we have vector A, which is an array, and it is what you call also a column vector. Yeah, so all the entries are now in a column. So you have one column and you have 4 rows in this case. So an example of vectorization is I could now apply a function to this vector A. For instance, I could define a square root vector, NP square root, and I just pass in my vector. And you see now you get the vector. I can also use the same logic to create a matrix. So for instance, I could use the following. I can say matrix, it's NP zeros, and then in brackets, inside brackets, so that's a tuple actually inside, 3, 4. The first entry refers to rows, the second one refers to columns. So this gives you a matrix with 3 rows and 4 columns. So if we just run this, we have now here the matrix. And again, we can use indexing to assign values. Again, of course, you note Python is counting from 0. So if we just do that, we now update one entry, so that is 0 refers to your first row and 1 refers to your second column. Good. Very often in programming it's useful to understand the shape of a matrix and its size. For instance, we can just do a print statement here, and we can explore the shape of a matrix. I just refer here to matrix. This is my object. I use the dot operator and use shape. So again, if you haven't seen the video on OOP, have a look. So here we have it. So we get a tuple as a return, 3, 4. So that tells me you have 3 rows and 4 columns. So that's useful. And of course, then you can, because it's a tuple, you can now index. So for instance, I can do something like this. I can refer to the second entry of the tuple, which would give me the number of columns. Now size refers to all the entries. So for instance, if we have now this 3 by 4 matrix, I just now write this down here and put in some numbers. Okay, so and I have 4 columns. It's always nice to visualize it. So that's my 3 by 4 matrix. And if I want to pre-multiply a vector to it, you have to think about matrix multiplication. Now these are the things as a data scientist which are useful. Yeah, so you don't have to have a degree in mathematics, but a bit of linear algebra goes a long way. So for multiplication, to if you pre-multiply, so putting something in front, I have to match my dimensions. Yeah, so I have to match this dimension 3. So I need here 3 columns, and I need anything in front. Yeah, so if I do a vector, it could be a 1 times 3 vector. This is a so-called row vector. Now I multiply row by column. 1 times 1 plus 1 times 0 plus 1 times 2. The column sums, yeah, so that's then 7, and that should be 12. Good, moving back into it. So how do we do it? We use our shape. Yeah, so I could do ones, so this is my all one vector, np.ones, we already have used that, and now inside I specify the tuple. I have 1 row and I have the matrix shape, and refer now to the rows of the matrix because they have to match. So that should give me the row vector. So if I now go into ones, I have now, you see this, a row vector with 3 entries. So it's matching the structure I want. Yeah, so that's helpful, and I want to pre-multiply this. So I do now a matrix multiplication. Good, matrix multiplication, I just call this the new matrix. Yeah, so that's the new matrix, and that's np.mat_mul for multiplication. I take ones because that's pre-multiplied, and then I put our matrix next to each other. Yeah, and I just execute that. And it gives me a new matrix. Of course, it's a very boring one because I just have 1 entry of 7, so it's not massively interesting. Yeah, but it's working. Yeah, so this is a very common use of shape in these matrix operations. Good. The next and useful thing to know is the identity matrix, because we use it a lot also in matrix calculations. So identity matrix, how do I do that? So I just call this the matrix identity, and it's simply np.i5, also dimension is here 5. Then we can also do in a very quick way some descriptive statistics. So if we have, for instance, data entries in our matrix, we can use descriptives. We can do a few print statements here, and we can refer to matrix.sum, open close brackets. So that's 1, simply summing up all these entries. Then we can look at the mean, for instance, and we can do the standard deviation. Very often we need an X dimension. There are different ways to do this. So for instance, we can do an index using the NumPy Arrange function which has a starting value, an endpoint which is exclusive, and a step. And the step is fixed, so that's one way to do it. Let me just run this. Another way to do it is to use a different index. I just call this now LDX, and this is using linspace, which is actually my favorite. We have a starting value, we have an endpoint which is included here, and we have the number of steps. Python selects the step size using equally spaced steps. First one using arange, and you have this fixed step size. And you exclude the last one, and the other one is using the step size selected by Python and doing this in 100 steps. Yeah, and we have included the 10 in this case. The next thing what I would like to show is about combining some data structures. So I just start with examples. I have a matrix A, so NP array, so I assign here my array, and then in rectangular brackets I specify the structure, and now I have a matrix, so I need another round of rectangular brackets. So that's matrix A. So here we are. So we have the first row 1, 2, 3, and then we have a second row, and then we are lazy, we just copy paste that, and we replace a few numbers, and we call this matrix B, and we can specify here a separator, and here you are. So you have here 1, 2, 3 and 3, 6, 8, and then you have a second matrix. Yeah, to combine these various matrices. The first one is a horizontal stack, H stack, so that's the horizontal stack, matrix A and matrix B, so that is combining them horizontally. Now this would, for instance, mean in a data sense that you merge two data sets where you don't have now more observations, so not more rows, but you have more columns, which means you merge more variables into it. Another one to look at is the vertical stack, so it's just doing the whole thing vertically. So that, for instance, would imply that the additional data refers to new observations, and so you get more rows. Now another interesting discussion is the ravel versus the flatten function. That's interesting, and it's a bit tricky. And I just do here my matrix A, and I use now the flatten method. You see how it's done. Yeah, you call this method after using the dot operator. I use now flatten first, and you see so everything is flattened into one single dimension. In this case you have one row, and you include all the entries. Now the ravel is looking the same, but actually behaving quite differently. Good, so it all refers to our matrix A, so have in mind that's our matrix A. So this is how matrix A looks like, and then we have our ravel 1, which is all of that, so that's good, and we have our flattened one, which is up here, so that's the flat one. So they look identical, yeah, it looks perfectly fine. However, if we start changing things, things go a little bit interesting. Good, let's start with the flat, and I change an entry, yeah, the third entry. So I do indexing here, and I just put this up to 99. So I do that, I run it, and well, what you expect, of course, is that now my flat is changed in the index position 2 to 99. Okay. Now when you go back to the original matrix, nothing has happened. Well, this is what you would expect, wouldn't you? Okay, let's see what happens if I do this for ravel. So if I do exactly the same for ravel, what's happening here? Okay, I run this. Okay, that's great. So let me go now to the ravel one. So as expected, index position 2 is changed. Great. And now let's go to the original matrix, and on a sudden, oops, it's changing. And that is very, very tricky. So you have to have in mind, when you use ravel, it's different from flatten. Yeah, flatten is always a copy of the original object. Yeah, ravel is not. Yeah, it changes the original object. If you intend to do this, that's fine, but quite often you don't intend to do this. So you have to be very careful. That's all I wanted to cover. So we had a nice little chat about NumPy. In the next one, we go more into data visualization and we look into some very simple simulations which can be done very effectively in NumPy. I'll see you in the next one.